Welcome to an example on how to use Green's theorem to evaluate a line integral. We want to evaluate the given line integral where the curve C is the boundary of the region between the circles given by x squared plus y squared equals 4 and x squared plus y squared equals 9. Let's begin by reviewing Green's theorem. Green's theorem states that if we have a simply connected piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R, meaning the region R is always on the left of the curve, then if the vector field F has components P and Q, where both have continuous first-order partial derivatives, then the line integral along the curve C of F dot differential R, or the line integral in differential form, is equal to the double integral over the region R of the partial of Q with respect to X minus the partial of P with respect to Y, differential A. And when the path of integration satisfies Green's theorem, we can denote the line integral in this form here where we put a little circle in the middle of the integral symbol. So going back to our example, notice how because the integral symbol does have this circle, we know the curve C does satisfy the conditions of Green's theorem, but I do want to spend a little bit more time explaining how this region R would satisfy Green's theorem based upon the definition. Remember earlier we discussed how Green's theorem states the curve C must be simply connected and piecewise smooth with a positive orientation, and here were three examples that we looked at. And we said this region here, which looks somewhat like our region, is not simply connected, and therefore it might seem Green's theorem does not apply. But it still does, and let's see why. If we can trace out this region with a piecewise smooth curve with a positive orientation, meaning the region R is always on the left side of the curve, then Green's theorem would apply. And notice how I designated four curves here. The outer curve along the larger circle is C sub 1, and then we have C sub 2, the curve from the outer circle to the inner circle, and then we have curve C sub 3 around the inner circle, and then we have the opposite of C sub 2 going back out from the inner circle to the outer circle. I labeled this negative C sub 2 because notice how it's the opposite direction of curve C sub 2. So notice how if we were to start here and trace around the outer circle, this is a positive orientation because the region R is on the left of the curve. And then we stop here and go to the inner circle. And then notice how we're going clockwise around the inner circle, but still the region R is on the left side of the curve, and therefore we still have a positive orientation. And then we go back over to here and back out to the outer circle to make a simply connected piecewise smooth curve that traces out the region R, which means our curve C could be defined as C sub 1 plus C sub 2 plus C sub 3 plus the opposite of C sub 2, and simplifying we get the curve C is equal to C sub 1 plus C sub 3. So this is one way we can trace out the region R to satisfy Green's theorem. But notice how this also shows us that if we have a region with a hole in it, as long as the outer region has a counterclockwise orientation and the inner region has a clockwise orientation, both curves still have a positive orientation because the region R is on the left, and therefore the curve C would just be the sum of the outer curve and the inner curves. And also notice how if the inner curve had a counterclockwise orientation, the curve C would have to be C sub 1 minus C sub 3. Again, all this isn't necessary for this example because we're told by this little circle in the integral symbol, the condition of Green's theorem for curve C has already been met. So starting with the given line integral along the curve C that satisfies Green's theorem, we have y cubed dx minus x cubed dy. So this tells us that p is equal to y cubed and q is equal to negative x cubed. And now let's go ahead and find the partial of q with respect to x and the partial of p with respect to y. So the partial of q with respect to x is the derivative of negative x to the third with respect to x, which is negative 3x squared. And now let's find the partial of p with respect to y, which is the derivative of y cubed with respect to y, which would be 3y squared. So now applying Green's theorem, this line integral is equal to the double integral over the region R of the partial of q with respect to x, which is negative 3x squared, minus the partial of p with respect to y, which is 3y squared, differential a. But now because the region R is bounded between two circles, let's write the double integral in polar form, where we know differential a is equal to r dr d theta. And notice how here, if we factor out negative 3, we would have negative 3 times the quantity x squared plus y squared, and x squared plus y squared is equal to r squared. So in polar form, we'd have the double integral over the region R of negative 3 r squared, and again, differential a is equal to r dr d theta. And now let's determine this integration for r and theta. Because the region R is bounded between these two circles, where the inner circle has a radius of 2 and the outer circle has a radius of 3, the limit integration for R are going to be from 2 to 3. And then trace out the region between these two circles, the limit integration for theta would be from 0 to 2 pi all the way around the circle. Now let's evaluate this on the next slide. Let's rewrite the integrand function as negative 3r cubed. Integrating with respect to r first, we would have an antiderivative of negative 3 times r to the fourth divided by 4, or negative 3/4 r to the fourth. Now to find big F of b minus big F of a, let's factor out the negative 3/4, and then we'd have 3 to the fourth minus 2 to the fourth. So 3 to the fourth minus 2 to the fourth is equal to 65. And so negative 3 times 65 is equal to negative 195. And we have the integral from 0 to 2 pi of negative 195 fourths d theta. Integrating with respect to theta, we have negative 195 fourths theta. And again, big F of b minus big F of a. So we're going to have negative 195 fourths times 2 pi minus 0. Notice the 2 and the 4 simplify, so the exact value is negative 195 halves pi, which as a decimal would be approximately negative 306.3053. I hope you found this helpful.